Hello everyone, this is our test 2 from this year, 2020, question 1A. You have to read the question. It's all expansion compression of ideal gas question. Given the following variables, you have number of moles. You're given the initial temperature, 25 degrees. You're also told that this is an isothermal process, meaning that our temperature is not going to change. So you also know T2. You're given the initial pressure. You're given the external pressure. And you're told that the final volume is twice as much as the initial volume. And you want to find heat, work, delta U, and delta H. You're also told that this is a monatomic gas. So your CV will be 3/2 R, and that's 1/2 R per degree of freedom. And your CP is another R, so now 5/2 R on top of that. So the really important point about this is the type of process stands out at you right away, and that is an isothermal process, which means that delta T equals 0 right away. If you look at what equations rely on that, remember under any conditions, expansion or compression of ideal gases, delta Q equals this equation right here. So it doesn't matter that it's constant volume process. It's just when we work this out in class, you guys go through the derivations, this is the equation under any conditions. Also, delta H equals NCP delta T. Doesn't have to be under constant pressure conditions. So right off the bat, if you have a 0 and a 0, that's telling us delta U equals 0 and delta H equals 0. So we just have 2 out of our 4 variables taken care of. Next things, remember now our equation for, we focus on, well, you can look at the other equation for delta U equals Q plus W. So we're into the case now where Q is going to equal minus W. Q is a little bit harder to find, but W, remember your equation for that one, that's minus P external delta V. Okay. So delta V, if we just want to write this out too, because I don't actually have any numbers here, that's minus P external V2 minus V1. And if V2 is 2 V1s, then this just boils down to minus P external V1. There's our equation for work. We have P external. We don't have V1. This is an ideal gas question, and if you look and see what else you have N, T1, and P1. So using our ideal gas equation, P1 V1 equals nRT, we should be able to solve for V1. I am going to write these values in here because we're going to go over units. So we have 2.5 moles. Now the R we're going to use is going to depend on what units we're going to use in this. We have pascals for our pressure. We don't have a volume unit yet, but it's going to tell us what unit we're going to get for that case. So if we want to stick to pascals, the R that you're going to use is 8.314. Remember, a joule is a Pascal meter cubed. Okay, so we use 8.314. I'll write it in as Pascal meter cubed. That's okay to do that. Per mole Kelvin. And then T, switch that to Kelvin, we have 298.15 Kelvin. And all of that over our P1 in pascals. 10 to the 5 pascals. So when you work this out, you're going to get a value for V1 of 0.0496 meters cubed. Okay. Now, if you were to plug that back in to our work equation, you're going to find a value for the work of minus 754 joules, which means that our Q is going to be plus 754 joules. There you go.